Today I'm going to be talking about eigenvalues and eigenvectors. Now, I know a lot of people tend to shy away from eigenvalues and eigenvectors. They tend to be a little bit scared of them and groan when it's mentioned in a class, but I want to set it straight right now that you are wrong and they are important, so we are going to learn them. So, the big situation with eigenvalues is that they are important because well, I guess we kind of have to set the scene first. So, what does this concept mean? Basically, what we're doing is we're taking a matrix, right, and we're multiplying it by some vector. We're going to call x. So we're going to say this is a vector. That's a terrible arrow, and we want this to be equal to just a simple scalar value also multiplied by this vector x. So if this x were perhaps 1, 2, and we had some value that was perhaps 3, then if you multiply 3, a scalar, by a vector 1, 2, then we would get the new vector, which would be 3, 6. And we want to have a matrix that satisfies that equation. Well, that may be a little bit difficult to do in the reverse direction, but what we can do is in the other direction, we can take a matrix that we already know and find the vector and the values that when you multiply the vector by the matrix, it is the same as multiplying the vector by a value. So that might be a little bit confusing right off the start, but that's the goal we're shooting for with this discussion here. So first off, I want to say that, well, actually, no, let's get into it first. So we're just going to take our matrix to be something simple, and we're going to say that we have a matrix which is in the form 4, 2, 2, 4. Now, you will notice that this is symmetric along the diagonals. Now, that is not necessarily too important in terms of actually finding eigenvectors or eigenvalues, but it is nice, and I will say right off the bat that I come from a mechanical engineering vibrations background, so that tends to be what I will be focusing on when it comes to notation and sign convention. But we are going to just write out this equation the way that we see this above. So this is a matrix I've selected, and this will work with any matrix of any size as long as you correctly size all the other components. So because we have a 2 by 2 matrix, we have to multiply that by a vector of 2 by 1. So we're going to call this x1 and x2. That is a 2. And then this is going to be equal to our scalar lambda times some value that is x1, some vector x1, x2. So as you can see, this is the same vector x that we are having above. We have our scalar here, lambda, and we have our matrix that we're going to work with. Now, the first thing we have to do is deal with the situation that at the moment we have a scalar on this side and a matrix on this side. So those two can't really talk to each other too much. You can multiply a scalar by a metric. Sorry, the other way around. You can multiply a matrix by a scalar, and you will just multiply all the values in that matrix. But for the time being, we want this to be an equal equation. So we have to reconfigure it so that there is actually a matrix on both sides. And there's a little trick you can do to achieve this. So we want a matrix that when multiplied by this, when multiplied to this vector, does nothing, absolutely nothing. So what we can do, so that's basically like multiplying a number by 1. We want to have something that just doesn't change it. It's something that we use a lot of times when we're trying to convert fractions into something more workable. You can multiply something by a number over itself, and it's not really changing the value of the fraction, but it may change how we deal with things. So if we have our matrix over here, 4, 2, 2, 4, and then we have our vector. The matrix that we are going to add to this side is actually the matrix 1, 0, 0, 1. And the reason that we're doing this is, if you think about it, when you multiply a vector by a matrix, what do? Well, you take the vector itself and multiply it by the rows of the matrix, and it spits out a new vector. So in order to find the first term of this vector, you would multiply this column by the row of the vector, so it would be 1 times x1 and 0 times x2. So that's going to give you x1. And when you multiply the vector by the bottom row, then we are going to have 0 times x1 and 1 times x2. So the vector we get back is x1 times x1 x2, which is exactly the vector that we have here. So we have successfully achieved, in the general case, the matrix that we need. Now, this is true for all sizes. So if you have perhaps a 3 by 3 matrix or a 3 by 1 vector to initially start out, you can just choose a 3 by 3 matrix where all of the main diagonal, that is the top left to the bottom right, are 1s and the rest are 0s, and that will give you your vector, your matrix that will not change a vector when multiplied by it. So I believe this is somewhat called a identity matrix, just because it has that property. So what we can do now that we've expanded this equation a little bit is, as I mentioned, you can multiply a scalar into a matrix. So that's exactly what we're going to do. We're going to continue our equation. Sorry, this is a 2, 2, 4, and then our vector x1, x2. I am bad at drawing 2's today. And now we are going to multiply this scalar into this matrix. So if we have our value here, we are going to have lambda 0, 0, lambda, and then we have x1 and x2. And so here, now we have a matrix times a vector, and a matrix times a vector. So it's a little bit easier to see how this might work out in the long run. So I'm actually going to grab this guy, and we are going to move on to a clean sheet so that we can continue working on this. So we're going to copy that and go to a new page, and then we will paste it. And so there's a little bit of some weird stuff over there at the top, but that's not a big deal. Okay, so maybe I can just erase it. So we are just continuing solving this equation. So what would you do now? Well, we have this x vector on both sides, and we need to get all of the x vector to one side and the the other values to the other side. Now, in this case, when we move this to the other side, we are going to have a 0 vector over here. So that's something to keep in mind. But what we can do is we can simply subtract to the other side. So if we then do that, you can think of this somewhat like, let's say, if we had a times x is equal to b times x. Well, what will we have when we do this conversion? So we're going to have the quantity a minus b all times x is equal to 0. And that's exactly what we're going to have from this matrix equation. So we are going to have our matrix M here, and what we're going to call our lambda I for the identity matrix over here. And we're going to have our value M minus lambda I times our x matrix, our x vector. I'm probably going to get that screwed up a little bit. Multiplied by the 0 vector, because there's now nothing on the other side. And this is a vector because we are considering two different simultaneous situations with this vector. So this is representing the vector 0, 0. So what does this mean? Well, we have to subtract the individual the places in each of these vectors. So the index 0, 0 for this vector is going to be subtracted from the index 0, 0 of this vector. Sorry, I keep saying vector and matrix. Focus on what I'm pointing at and not what I'm saying, I guess. So what we end up with is a larger matrix, and we are going to have 4 minus lambda, and then 2 minus 0 is just 2. Then we'll have 2 minus 0, which is just 2. And then we're going to have 4 minus lambda. Okay. And all of this, as mentioned before, is going to be multiplied by our x vector. And that is going to be equal to the 0 vector. Well, now we are getting somewhere. Because if we now have this situation here, we can try and figure out what these lambdas are equal to. Now, the way that we do this, and there are proofs out there for how this works. Just for keeping this simple, I'm just going to tell you how to do this, just for practical reasons. And then if you want to do some more research into it on why it works, then you can do that on your own. What we're going to do is we're going to set the determinant of this value equal to 0. Because there's two different situations that can happen here to get the 0 vector. We can have our actual vector here equal to 0, but that's an obvious case. We call that trivial. So we don't really care about that situation. We want this matrix to be equal to 0. And the only way that this matrix is equal to 0 is if the determinant of that so equal to 0 in the sense that multiplied by this vector we will get the 0 vector. The only way that we will get that is if the determinant is equal to 0. So what we are going to do is we're going to do the determinant of this big matrix here. So I did post a resource you can use in the, if you click on the icon, I'll probably have it pop out if you're watching this not live. And that is a video on how to do the determinant for a 2x2 matrix. But as I mentioned, this does scale to other sizes of matrices. So if you have a 3x3 or a 4x4 or so on, you just simply have to do the determinant of that larger matrix, and it'll be a little bit more complicated as you actually solve that equation out. But the determinant is going to be this value times this value minus this value times this value. So we are actually going to have lambda squared, and then we're going to have minus 8 lambda, and then we have plus 16, and then, as I mentioned, 2 times 2 is 4, but we are subtracting that, so we are going to have this equation equal to 0. So lambda squared minus 8 lambda plus 12 is equal to 0. Now, in the general case, you can always do the quadratic equation at this point. Now, this equation is actually quite easily factored. So this is actually equal to lambda minus 2 times lambda minus 6. And as we know from algebra, this means that our two scalar values are the number 2 and the number 6. So what this means is that our eigenvalues are 2 and 6. So we've actually found the actual scalar value that can be multiplied by into this this vector that we don't know yet. That would be the same as this matrix multiplying into this vector that we don't know yet. So as I mentioned, we don't know the vector yet. So we're going to keep this 2 and 6 in mind, and we're going to look for the actual vector. So the way that we do this, let's go to a new page. Actually, I want to grab this equation right here because we're going to need that. So grab this. You may hear some dog barking in the background. I cannot currently attend to that, so it will continue. So if we get a new screen up and we paste this equation up here, I mentioned that this will be important. And the reason for this is we are actually going to use this equation to solve for the vector that corresponds with the individual eigenvalues, because as I mentioned, we want this equation to equal the 0 vector. So what we need to do is we need to solve these two equations, because if you think about it, this is actually a system of equations. If you multiply these vectors together, we're actually going to get two equations. So what we can do is we can do that right now without plugging anything in first. So if we multiply these two equations, then we're going to get 4 minus lambda times x1 plus 2x2 is equal to 0. So that's our first equation. And then our second equation is going to be 2x1 plus 4 minus lambda x2 is equal to 0. Now something odd is going to happen when we start plugging things in, and you'll see that as we do this. So let's plug in our first eigenvalue. So we're going to write these over here, that lambda is equal to 2 and 6. We're going to plug in our first value of 2. So if we plug in 2 to this first equation, what we get is 4 minus lambda, which is 2, which gives us 2. So we are going to have 2x1 plus 2x2, sorry, the 2 is down here, is equal to 0. And if we plug 2 into this second equation for lambda, then we are going to have 2x1 plus 2x2 is equal to 0. Now, you may realize that this is somewhat of a problem when we're actually trying to solve for values in a system of equations, because it turns out that we only have one equation to work with. These two equations are the same equation. Sometimes what you'll see is that you will have a scalar multiplied into one. So maybe this would be 4x1 plus 4x2 is equal to 0. But in the end, it's the same equation. You can just factor that out. Like in this case, you could factor out the 2. You would just have x1 plus x2 is equal to 0. So what does this mean? Well, it goes back to actually looking at what the eigenvalues and eigenvectors are. So if we look at our equation of mx is equal to lambda x, what this means is that in this specific case, the vector that we are choosing to have multiplied by this matrix is actually not rotating. Now that may not be too intrinsically visual, so I've actually put a resource to a geometric visualization of the eigenvalues and eigenvectors up in the eye icon if you want to click on that. But what this means is instead, so if we have a vector like so, correct, and this is our x vector, when we multiply by a scalar, this vector does not rotate or anything. It simply grows or shrinks based off of the value of that vector. So if that vector is greater than 1, then it increases. If it's between 1 and 0, then it shrinks, and then it's the same, but it flips also if there's a negative involved. So what we are actually finding is an entire family of vectors that lie along some line. Because that is what we are getting. We're getting the actual line that is this vector lies on. And so what that means is any vector that is along the line of 2x1 plus 2x2 is equal to 0 will actually satisfy this equation and be an eigenvector. So we are going to solve to find out what those vectors are. So we are going to give our self some more space. So if we look at what this equation is, so we said that is 2x1 plus 2x2 is equal to 0. Well, we can just solve this for the ratio of what x1 is to x2. So what that means is we're actually trying to find the slope of this equation, and then we can use that to just give one answer out of the infinitely many possible answers. So I'm actually going to solve this for x1 over x2. So we want to find how far we go in the x2 direction every time we take a step in the x1 direction. And the way we do that is we can move x2 over to one side, and so we're going to have, let's say this, we'll say 2x2 is equal to negative 2x1. So that means that if we have x2 over x1, this is going to be equal to the value 1 because it's negative 2 over 2. So what this, as I mentioned, this gives us what the slope of that equation is. But what we can do is we can just choose an answer for x1 and see what the value of x2 would be in that circumstance. So if our value of x1 is 1, then our value for x2 is actually going to be negative 1. So that means that for every step in the x1 direction, we're actually going down a value in the x2 direction. So this is a vector. So this is a vector that satisfies our original equation, and we can actually go back and check that if you want. So we could say that, oh, well, I mean, we are checking that intrinsically by plugging it into this equation. But a lot of people will tend to want to normalize this vector. What that means is they will try to get a vector that when you plug the values into x1 squared plus x2 squared, this is equal to 1. So you can just imagine that this is a vector of this direction, if this is x1 and this is x2, and the value on the unit circle that is talking about a 45-degree angle in the fourth quadrant, so this is 45 degrees, is the value, I believe that would be root 2 over 2 negative root 2 over 2. So that is our first vector, and we can actually go back and solve for the second vector. Now I'm actually going to only write out the equation once this time because we've already talked about the fact that eigenvalues, when plugged into that matrix equation, only give us one equation in the long run. So if we go back to our equation of 4 minus lambda x1, that's not x prime, x1 plus 2x2 is equal to 0, and we plug in our other eigenvalue of 6, then we're actually going to get negative 2x1 plus 2x2 is equal to 0. And what we can do with this is we can do the same thing. So we want to find what x2 over x1 is going to be, and because there is a negative 2 here now, we are actually going to have positive 1 because we move the x1 over to the other side, divide, and we find that our value is x1. So this is associated with the vector 1, 1, or if you want to normalize this, it would be the value 2, root 2 over 2, root 2 over 2. So this would be a vector in the positive direction. So as I mentioned, you can always remember that this is a vector like this along this line. We are going to have a vector like so along this line that is orthogonal to the other vector. So here is how we solve for the eigenvalues and eigenvectors of a matrix. Now these vectors and values can be useful, as I mentioned, in vibrations because what we can find is we can actually find the natural frequency of a vibrating fixture, and we can actually or the many natural frequencies of a vibrating fixture, and we can find the vibrational nodes of that vibrating fixture. So if we have just to give you an idea, if you have perhaps some system where there is a spring and there's 3 springs and 2 masses, what can happen is we'll have these two vibrational modes that we found, where one is 1, negative 1, and one is 1, 1. And so what 1, 1 means is that we can move both of these initially in the same direction, and they will continue to move in unison. This is actually if the entire system is symmetrical. And if we have the other situation, then this arrow is going to be pointed in the opposite direction because we have negative 1. So they will be moving like so. So what ends up happening is that actually all situations that are that can happen with this 2 degree of freedom system are combinations of these. But perhaps that should be saved for another video. So this is how you solve for eigenvalues and eigenvectors. If you have any more questions about how to actually, or if you're confused about any particular part of this video, please feel free to leave questions and comments in the comment section, and I will make sure to try and clarify. If there tends to be a significant misunderstanding with any part of the video, I may attempt to clarify that in a follow-up video, and I'm sure you will see a link to that at the end of this video, assuming that the video I am referring to has already been made. So I want to thank you guys for watching this section, and I'm going to be moving on to my random drawing section, so bear with me.